Thank you very much. Internet is the basic venue for the communication, and it is not bad. However, oftentimes users face some toxic content. For example, the chatbots that are trained based on commentaries and text from the network can have a too standardized response, and this will lead to negative reaction of the users. And usually people are talking based on emotions, and if you block the offensive phrases, it will lead to more aggression. Selecting and recognizing these words and expressions, so defensive words and expression, and replacing them with better words without losing the sense is a relevant topic. And Alexander Panchenko from the Center of AI Technologies of Skoltech will talk more about that.
Hello. Thank you. The project that I will be talking about is about detoxification of text, supported by the research center of MTS. And first things first, I wanted to thank so many of my colleagues, engineers, postgrads, research fellows who contributed so much to this project, and primarily David Daley, Darina Dementeva, and Varvara Logachova. I also wanted to thank Darina for helping me with the slides. After the project, we published a lot of papers, 16 to be specific, in international journals, in collections of articles for conferences. We published in ASCL and EMNLP, and if you're interested, if you want to learn more about the technical aspects that I simply won't have enough time to cover in my presentation today, feel free to look up those publications. Unfortunately, toxicity is the norm in today's internet life. This is the way of communication that is commonplace, that is everywhere, and there are different solutions to this problem. Solutions can be simple and straightforward, simply blocking, using a selection of specific words. That is the solution used in Instagram, or classification of posts, toxic posts that contain signs of toxicity in different threads. Usually this results in censorship, blocking posts, blocking users who publish those posts. The technology of detoxification of texts suggests an alternative to such direct censorship. Specifically, we could offer a commenting user to rephrase the comment. This way, we will not be censoring them. An alternative use case in detoxification is using it in AI/ML models such as GPT, generating text. There's been this high-profile case with the chatbot called Oleg, developed by Tinkoff Bank, when the chatbot suggested a client to simply cut off her fingers because the client was experiencing troubles with identification using the fingerprints. In situations like this, technology directly affects and could even ruin the reputation of a company. What is the solution we are talking about? We have an input text in a certain style. The goal is to generate text in a selected style to maintain the content and to have the text be grammatically correct. In detoxification of text, we are talking about transition from toxic style marker to neutral or non-toxic. The content should be preserved as much as possible. And the result, of course, should be, as I said, grammatically correct. A few examples of such rewordings. You can see them on the slide. Also, there are two big schools of thought, two big approaches based on parallel data and non-parallel data. One of the approaches suggested in literature is called delete, retrieve, generate. In this approach, you use a big set of texts, non-labeled. Positive text could be transformed into negative and the other way around. To do that, we look for colorful markers, explicit markers, and then in the simplest example, the marker from the initial text can be substituted for a marker retrieved from another text, a similar text. Or we could use recurrent neural networks, where the marker identified in the background collection could be replaced and used for generation. An alternative suggested once again in literature is mask and fill. In the original text, we once again look for toxicity markers, so words that are classified as toxic by the classifier. Then we use the masking language models, which masks the markers and replaces them with lexical units that are the closest in content by content, by meaning, but that are less toxic. We had this publication in the EMNLP, where we use pre-trained paraphraser. We use special additionally trained models trained to simulate a specific style. This is different from previous approaches. It does not perform targeted replacements, but it rather rephrases the entire sentence. It then re-ranks the results of its work depending on the toxicity or the non-toxicity of the resulting tokens. This is an interesting approach because it does not require a parallel collection of texts, and also with the majority of approaches suggested in literature, as opposed to them, we're not using parallel collection. The reason is simple. Some types, some sets are simply not that easily accessible. Sec-to-sec approach is another good example where you take a text and you rephrase it from one language into the other. It would seem natural to just use it for rephrasing the text, for making the text non-toxic. We can use a lot of pre-trained neural networks, GPT, but to perform this task, so seemingly we have the toolkit, but previously we did not have parallel collections of text that we could use for pre-training our models. Two collections that we had, the Bible dataset and the GYAFC dataset. The Bible dataset is the biggest collection of texts in terms of language coverage, but the sheer number of languages that it covers. And in this case, we can have different versions of the Bible in English, for example, in Old English. We could convert that to modern English. The GYAFC dataset translates a non-formal utterance into a more formal one. So what we had available were big collections of texts, which were labeled by tonality and toxicity, but which were not parallel. In the Para-Detox article that was presented in May this year in Dublin at the ACL conference, we say that we have developed this technology which helps easily and cheaply create parallel collections of texts, parallel corpuses. Our hypothesis was that we should not create models that are not based on parallel corpuses, but rather we need a technology that would help us get parallel corpus. We were guided by several criteria. We wanted a corpus where for each toxic text we could have between 1 and 3 rephrasings, The content, once again, should be equivalent, so the message of the author, the idea of the author should be preserved. The style of the text should be obviously non-toxic, and the grammatical correctness should be preserved. The idea of toxicity is a tricky one. A lot of definitions, a lot of data sets that are inconsistently labeled. In our project, we decided to adopt a simple subset of this concept, the toxicity that can be rephrased in terms of style. So, for example, if someone makes this utterance somewhere along the lines of people that belong to group X are not very good, you cannot really replace some parts of it with equivalent phrases and make it non-toxic. So we would remove such utterances from our data set, and we would keep those that can be rephrased successfully into their non-toxic versions. So we took the texts, we split them up, we filtered them, we selected texts that are not too long, not too short, and we created a pipeline for crowdsourcing. It included 3 problems. The first problem was about rephrasing. So a person would get a text, the text was toxic, and we asked them to rephrase them in a non-toxic way. Very, very simple. They could refuse to rephrase if, for example, they thought that rephrasing was not possible. The trick was that we were not paying for this. Instead, we had 2 other problems where we would analyze the results of rephrasing. First, we would check whether the generated rephrased text was equivalent content-wise. If it was not, we would discard it and we would not pay the user. And we would also check whether the rephrased text was non-toxic. The overall para-detox pipeline was like this. The input text, we ask the user to rephrase it, we perform 2 checks, and then we repeat this procedure twice to get verifiable results. Once we have completed the 2 checks successfully, that's when we can pay the user. Quality control is absolutely crucial here, meaning that we need to make sure that the users are native speakers in the language. We also need to make sure that they have completed training and examination. We need to test them. We need to offer pretty complex tests, pretty difficult ones to select the best. We have 3 to 5 annotators that overlap, and we also need to have some control during tasks. Last but not least, we need to sort out the best, the most valid answers, because otherwise in the data set there will be deficient data and we will not be able to train the model successfully. We had the data set for the English language, and also in the Russian language we trained 2 detoxification systems last year. All the data are available free of charge. There is also a description of it in the form of articles. You are free to use them in your experiments, in your developments. So for English, for the English model, we collected 12,000 unique sentences with 1 to 3 rephrased versions, and 8,500 sentences for the Russian model. The cost of creating this corpus for the English and the Russian languages was less than $1,000. Compare this to the cost of work of a data scientist or a researcher, you will see that clearly this is very, very affordable. These are the examples that we ended up with for the English language. As you can see, the rephrased sentences are the same in meaning, but they are devoid of any toxic words. And these are the examples for the Russian language. This is a parallel corpus, same as you would use for machine learning model training. And it would seem natural to use it for sequence-to-sequence models and machine translation models. We talk more in our articles about the models that we were using. One is ContBERT. ContBERT looks for toxic words in the text. It then masks them and references a pre-trained model to replace the masked words with non-toxic words, and does the re-ranking. Another obvious task is to use the dictionary to remove toxic words or defamatory words. Other models that we used were ParaGDI, zero-shot, sequence-to-sequence, and zero-shot GPT. Our experiments were based on deep pre-trained models, transform-based, GPT-2, T5, and BART. For assessments in our experiments, we used several metrics. The first metric was the style transfer accuracy, second content similarity, and the other two are fluency and grammar correctness. All the metrics were put together in a score, the joint score, representing the overall quality. We used the same set of metrics for the Russian language. And this gave us the toolkit to automatically assess the quality of models, translating from toxic to non-toxic. In addition to these metrics, we also used manual evaluation. Namely, we used, once again, crowdsourcing to assess all three criteria: non-toxicity, style equivalence, and grammatical correctness, computed using classifiers, pre-trained classifiers based on BERT for toxicity, or BERT-based pre-trained classifier for fluency assessment. With manual evaluation, we asked humans for their opinion for assessment. These are the results of our experiments. As you can see, approaches based on deep pre-trained models using our para-detox corpus are way ahead of any alternative solutions. The approaches that use the non-parallel corpus, they generate results that are way worse. Based on automated and other metrics, we were able to demonstrate the advantage of our approach over all the analogs. This slide shows one of the examples, the original column with the original results of different models. As you can see from this slide, the sequence-to-sequence model is very accurately rephrasing, preserving the content, and removing all the toxic elements. Compare that to ContBERT, for example. They perform very locally and they often break the structure of the sentence. This applies to the dictionary-based method, where we can just randomly remove a word. We insert another one that doesn't really connect to other words in the sentence, and the result is not particularly relevant. We got the same quality of results for the Russian language. This table shows that models that were trained using Russian language corpus with BRU-GPT, BRU-TP base and BRU-TP large are way ahead of other equivalent solutions. Same results with automated and manual evaluation. And a few examples of quality assessment. How big is the difference between different models? Our model, RUTP, RUTP5, and our competition.
We have also developed demo systems, and you can try to find a chatbot in Telegram. It's called Detoxification. Or you can go on a website, enter a phrase, and get a response. It works for both Russian and English, and it can give you an overall idea in terms of how the system works. We also have an APIs where you can integrate this technology in your pipelines. And obviously the models can also be downloaded and used through the interface. So you can go and play with these models and see the possible applications of these models for yourself. A few words about the future developments. We are working on multi-language and cross-language detoxifiers. So we talk about the translation and the change of the style. The text that is written in a toxic, offensive German language can be translated into Russian, removing the toxicity of this language, of the source. These systems can be trained easily and quite cheaply. It is important to say that all models that we have tested were trained in just one GPU during several hours. So this is a very available technology. You get a good corpora of texts for less than $1,000. You train it with one GPU. You train the model with one GPU, and you get the great technology that works perfectly. Another area is the attempt to make the marking more efficiently through a smarter sampling of these examples with the active learning model. Potentially it will help us to save even more and to create the process of building such corpora even more efficient. And you should not look at this technology only as a technology for detoxification. You can create any text corpora that you need. It will be quick and cheap, and if you can formulate your task as in a sequence-to-sequence mode, and you need some training data, you can use our developments. I would like to thank the organizers for inviting me here. If you want to participate as a MA student, doctorate student, engineer, or a researcher, please contact me and we will discuss the possible options. Thank you very much, Alexander. I'd like to take this opportunity and ask you whether you train the model so that the model change the phrases, but didn't you give the freedom to the AI? You know, some toxic words can be replaced with some other toxic words. We have a vocabulary of offensive language in Russian, for example. Didn't you think about that? Well, this is a paraphrasing task. There are many technologies, and there are parallel corpora of text when one text is in line with the other text and the sense of this text and all the other parameters of this text are equivalent, so we can use the current technologies. As for the vocabulary of Russian offensive language, we had tens of thousands of words and expressions in our offensive language glossary, but the vocabulary methods do not work properly because neural network approaches help to generate text that is much more expressive and natural. So it does not really kind of creates these things, right? But I think maybe it will be great to give some freedom to artificial intelligence so that it suggests its own solutions to some problems. Well, I beg to differ, because the success story of our project is that we limited the freedom of the AI. We put a very stringent task. You need to translate this sentence and have this result. And these are the requirements. If you put a proper task for the AI, the result will be great, the outcome will be great. And the lack of success or for other methods was related to the fact that the task was very loosely stated. So I believe in a very stringent problem requirements. The same for the engineer. If you make a great technical assignment for an engineer, they will make a great development. So you have some good results, but how can you use this technology in other languages? Is it difficult to do that? Yeah, thank you for the question. We are working on that exactly. And now we have the pre-trained networks that use dozens and even hundreds of languages. So using these models, we will be able to diversify the model without the use of a lot of parallel data. This is a very promising area, and those who are interested, please contact me and we'll work together. Yes, that's great. Thank you very much. And you seemingly have a lot of work to do still, but great results, great achievements. Thank you. Okay, and now the keynote speeches, keynote presentations are completed. And